Hello everyone, my name is Timothy Lee Grant and we are back at it again with another Leetcode problem. So we're going to be still here in binary search, continuing our journey on learning this topic. So let's minimize myself here and just go to the next easy. We're only doing easy, we're not going to push ourselves too much. Tomorrow we'll do a medium, but today just an easy. So looks like this is the next one that is not done yet. And it's yesterday we did the number 1, so now we're doing number 2. Perfect. Awesome. Let's give it a go. Okay, so 350. Intersection of two arrays, number 2. Given two integer arrays, nums1 and nums2, return an array of their intersection. Each element in the result must appear as many times as it shows in both arrays, and you may return the result in any order. Okay, so the difference here is this part right here. The result must appear as many times as it shows in both arrays. So this one, in the previous one, we had to worry about uniqueness, and we just said, okay, if we have some array like nums1 equals like this, like 1 1 1 1 1 2 4 5, kind of like this, and then we have nums2 is equal to list, and it's going to be like 1 1 3 8 6, whatever it is. There's 2 1s here, and there's 1 2 3 4 5 1s up here. So, but we only care about one value, or we only care that this 1 exists in both lists, and no matter how many times it actually appears, we don't really care. It doesn't matter to us. But in this time, we actually do care about how many values, how many numbers, or how many times a specific element appears in both. So for example, this one has 5 and this one has 2. So we want to take the lower of that number, right? So we want a 1 here, 1 here. Okay, cool. This element has a 1. Or the answer, we can do this answer right here. Answer is going to be a list, and we can say, okay, cool, let's add 1 to it. Now we say, okay, there's a 1 right here and a 1 right here, so there's another set of 1s. Awesome. Let's append that. Okay, so now we go, I'm at a 3. All right, that's different. Cool. So let me look here. Okay, we kind of missed our opportunity. There's a 1 here, so I can't add that 1 because it doesn't appear also in here. There's not 3 1s in this nums2. So I think actually I can use a very similar idea that I had in my last video, which was just to make sure that these lists are sorted, right? So I don't like this 6 here. I'm going to move the 6 to be right here, and then I'm just going to get rid of this. So I'm going to sort my list, okay? Then what's going to happen is I can just put my pointer here and put my pointer here. And then I'm going to say, are these numbers equal to each other? Okay, yes or no. And if they are equal to each other, I'm going to add that value to my answers list. And then what I'm going to do is I'm going to move my pointer over to here and over to here and say, all right, now let's check this one. Are these the same? Yes, they are. Okay, put it also in here. Okay, then I'm going to move my pointer here and move my pointer here. Then it says, they're not the same. Okay, so how do I move my pointer in this situation? Well, first off, I don't add anything to the list, to my answers list, but I move the lower value. So this 1 is smaller than 3. And therefore, because this list is sorted, I know that I need to try to catch up to 3. So I look here, still a 1. Okay, they're not the same, so I don't add anything. And then I move the lower index, so it's now here. 1 and 3 are not the same, so I don't add anything. Then I come here, there's a 2, okay. 2 and 3 are not the same, so I don't add anything. Then I come here, 4 and 3 are not the same, so I don't add anything. But then 3 is smaller than 4, so now I look at this 6 and say, okay, 6 and 4 are not the same thing, so I don't add anything. And then I move this 4 up to this 5 and say 5 and 6 are not the same thing. Now I move this 5, and now I'm outside the bounds of the array, and I know that the only intersection between these two lists is this 1 and this 1. So the way that I'll do this is I'm going to say, like, answer is going to be equal to a list, okay? And in the previous one, we actually made this a set, right? Because we didn't want unique, or we only wanted unique elements in this list. We didn't want to have duplicates. We didn't want 1 and 1, so we had it be a set. And then we just took that set and then converted it to a list. We don't want that. We want, in this time, a list so that we can put multiple of the same elements in this list. Okay, so now what are we going to do? We're just going to do pointer 1 equals pointer 2 equals 0. So we're going to start at the first index, okay? Then now I remember there was some no, we don't need to worry about that. That was a problem previous. There was some controversy that I ran into regarding index versus the actual element, but that was something else. I don't need to worry about that in this situation. I can just do while pointer 1 is less than the length of nums1 and pointer 2 is less than the length of nums2. Then we perform this operation. Let's get length of nums1, so length of nums1. Okay, length nums2 is going to be equal to length of nums2. Okay, then what we can do is just look at the element. So if, let's see, nums1 evaluated at pointer 1 is equal to nums2 evaluated at pointer 2, then what do we want to do? That's the case where we're looking here and we're looking here, okay? And they're the same element. It's a 1 and it's a 1. So we want to add that to our list. Okay, so let's do that. Answer dot append. And what are we appending? Just that number, right? Pointer 1. So we're looking here and we're looking here. We say, okay, they're both 1. So then we take this 1 here and put it in our answer list. Okay, awesome. Then what do we want to do? If they're both equal to each other, we want to move the pointer over to this one and to this one. So we want to move the pointer over to both of them. So that way we don't have one that counts multiple times, and then we have the weird case like if it was like this or something, and we have 1, and then we add this 1, and then we add this 1, because our pointer is staying here for some reason. No, we want both of them to move kind of in unison because we added that, and that's an intersection, right, that occurred in both lists, and we say, okay, we added that, it was in both, now we can't reuse anything. So let's, let me put that back, okay? So let's do that. So pointer 1 plus equals 1, pointer 2 plus equals 1, Okay, else if nums1 evaluated at pointer 1 is greater than nums2 evaluated at pointer 2. Okay, what is this case right here? What's this case? So that's the case that we're looking at this 3 right here and this 1 right here. Okay, so we're looking at that, and the question is, uh, which, actually that would be kind of, nums2 would be greater, but anyways, we can flip-flop it however we want. We just need to think about the logic and then implement it in the code. So which pointer do we need to move? So we don't want to move this one right here because there's a possibility that there is actually a 3 in here, right? There could be a 3 right there. And we want to make sure that we keep our pointer here, say, hey, hold on, let's keep looking. But can there ever be a 1 in nums2? Can there be another 1? No, there can't be, because nums2 and nums1 are both sorted. Now we haven't done that yet, but that's going to be, we can get that, right? Like nums1 equal dot sorted. I think it's like that. And nums2 dot sorted. I had to look up this syntax yesterday because I couldn't remember it, and now I'm like, okay, wait, hold on, what was the actual syntax? I know that it's sorted like that, but I think that it happens in place. I don't think I need to do like nums2 equals. I don't think so, but we'll fix it later. We care about logic here, okay? So there could be another 3 in this nums1 list because we're looking at this element which is smaller. So we want to move the smaller index, right? The value which is smaller. And we just said nums1, that value is smaller. So we want to increase the smaller pointer. So pointer 1 plus equals 1. And do we want to add anything? No. Else what does that mean? That means that nums1 is larger, so we need to increment the pointer at nums2. Okay, so pointer 2 plus equals 1. All right, so now we should just be able to return answer. I think that is the case. Let's check and see if we got any errors or logic. Okay, it didn't like that. Sorted. Did you mean sort? It could, maybe. Maybe that was the, maybe that was it. Okay. Nope. Penned. There we go. Okay. This is just syntax stuff. Let's see if the logic was correct. And there we go. Okay. Oh my goodness. That was awesome. That was awesome. I liked that. This isn't binary search though. Like, you see what I mean? Okay. So we solved it. Good. But there's something fishy going on right now. I'm going to go and look at the solutions and see what other people are kind of saying, because I feel like I want to make sure that I learn as much as I can from each of these problems. And I don't want to say like, oh, I solved it. I'm going to forget about it. I'm not going to look at it. I'm not going to do any. That's not the way I want to do it, right? Let's look at these and see. What's this? It's locked. Okay, that's great. Thank you. So what's going on here? Return self.intersect. Okay, that interesting. It seems kind of like a cheat right there, but okay. I mean, if it works, whatever. Um, so if the, hold on, what is this right here? If the length of nums1 is larger than the length of nums2, then we just return the intersection of nums1 and, okay. Why are we checking for this? So I'm trying to figure out this solution. It seems like obviously they're doing some check here, and that check should have some purpose, but I can't quite understand what the purpose right here is, because it seems like you could always just do this like return and then the intersect of the two, right? Why does nums1, why does the length of nums1 need to be larger, right? Why would it break if I had 999999999 right here? Like now nums2 is bigger. What is the problem? Okay. So if this is not the case, we don't hit that return and we come here. Counter, does it have like a helper function? So counter nums1. Okay. Answer is an empty list. Okay, so for x in nums2, so we're just iterating through all of the elements in nums2. Count of, not the index, this is in nums2, so it is the actual element in nums2. So we're indexing on, the element. Have you heard of such an arrangement? So if that's greater than 0, we append the element. Otherwise, we decrement the value which is at the... What a strange operation. And where does this counter come from? What is this? Okay, let's read the approach, because this is fascinating. Using hash map to store occurrences of elements in the nums1 array. Okay. Iterate x in nums2. Yeah, that's what we saw. Check if, okay, I mean that's kind of like like that's just, this line of code doesn't, or this line of text does not give me any new information. That's literally just what this means, right? Like iterate x in nums2 array. Okay, it doesn't say why or what this is accomplishing. Okay, if you've done a for loop, you know what that does, right? And this just says what a for loop does. So that doesn't actually help me. It doesn't say why, right? Check if this, like, yeah, that's how an if statement works. Then append x to our answers and decrease. Yes, like that's literally just like self-evident by, okay, yeah, that's what the code does. Doesn't say why. To optimize the space, we ensure length of nums1 is less than or equal to length of nums2 by swapping nums1 with nums2. Okay, so they're doing some kind of so I think this line of code is like for optimization, and they want to know that one array is smaller than the other so that they don't need to waste resources on an extremely large array if one is really small, right? Like, for example, I think what's going on is if nums1 was kind of like this. Kind of like this, where it was just one element, and then this one was crazy long, like a million elements here, or something like that. I think that's why they're doing it. I don't quite see the... So that's... Okay, so nums1, keep in mind, has one element, right? And we're iterating through all of the elements in nums1, so the shorter element, or the shorter list. So that kind of like, I can see the connection here. I don't see... let me just paste back in there that. So I don't see why... So I get that at this point in the code right here, we know that nums2 is smaller than, or smaller or equal to, so nums2 is smaller or equal to nums1. But why can we just do the return intersect here? But then we should be able to do like else return self intersection, and then maybe nums1, nums2. I don't... To optimize the space, we ensure that... Okay, let's actually, let's go here. Let's see. Like, and this is what I was looking at yesterday. We were doing a very... It was almost identical. It was essentially the same problem. But let's go to Copilot and ask, like, what is going on in this code? Okay, let's see what it has to say for itself. Here we go. Always... There we go. Okay, cool. This implementation is a concise and efficient solution to find the intersection of two arrays where each element in the result should appear as many times as it shows in both arrays. Here's a detailed breakdown of how the code works. Okay, cool. Argument swap. If nums1 is longer than nums2, the function swaps them by recursively calling itself with the arrangements reversed. Hold on. Self dot intersect. Oh, this is called intersect. So we're just calling ourselves our own function, and we're saying, nah, this nums2, we're gonna put that as nums1. We're just taking and switching the arguments. Now, why you couldn't... I guess it's like, from my perspective, the way I would have thought about it, right? Like, I think most people, maybe it's because I don't have a ton of, like, I'm not big brained, right? Like, maybe this is a big brain answer, but the way I would have done it was just like, temp equals nums1 dot copy, like this. Whoops. There we are. And then nums1 equals nums2 dot copy, like this. And then nums2 equals temp dot copy, like that. Something like this, right? And then now, obviously, you've created kind of like this temp thing, or the temp list, and that is not memory efficient, right? So I think what they're doing here is just more like a memory efficiency trick. Okay, that's actually pretty clever. I like that. That's pretty fun, isn't it? Right? Like, dang, nice. Okay, so then we're gonna get here, And it's going to happen in both cases, right? No matter if nums1 is larger or nums2 is larger, we just switch the parameters and force nums1 to be smaller. Wait, no, sorry. We force nums2 to be smaller. Okay, so we know that nums2 is smaller, so we can now uh, be confident in our path forward to say, okay, cool, nums2 is smaller. We can just look, we can take that as an assumption and try to keep that in mind to optimize our space and time complexity. Okay, nice. I like it. Okay, so count elements in nums1. Count equals counter. Counter creates a dictionary-like object. Okay, so this must be like a built-in Python function that I was unaware of. So counter creates a dictionary-like, okay, dictionary, there we go, like object where the keys are the elements of nums1 and the values are the count of those elements. So that's probably why they're indexing the element as the key and getting the value. Yo, what? How creative is this? How? I love this. Dude, who created this? Mr. My Tan Hip. This is amazing. Like, dude, I love this. Okay. So we're creating a dictionary, and or remember, like dictionaries like have whatever. So you have the key, right? And then you have your value, and the key is what you kind of you can put in, and then you that's like how you index your dictionaries or whatever, like my dictionary is going to be equal to this, right? And then you can add elements to it, and then you index it like my, and then indexed based off the key. So key, and this can be like 1 or 2 or 10, right? And then it returns back to you the value associated to that key, right? So what he's doing here is he is the key is going to be the number, right? This number, 1. Then the value is how many times it appears in this nums1, right? Nums1, which is the larger array. We know at this point, we know something like this, that nums1 is larger. And let's just say that there are a million fives out here, right? We can we don't need to iterate through all of that junk, because that the million fives is to our perspective junk, and iterating through that is just burning computation. It's increasing our time inefficiency, and we don't want a huge like space complexity either. So we're able to just like store one like value, it's 5, and then 2 million, right? It occurred 2 million times. That's, and all we need to do is store 2 numbers. So, okay. Then what we do is we come here. Now we go through each element in the smaller array, right? We don't want to iterate through the billion, million, trillion, however many data points in the larger one. No, we want to just go to the smaller one. Let's do that small nums nums2. So we iterate through each element in nums2. Bam, 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 bam. Now, what we do is we get this 1, okay? We have a 1, and we come here. So if, now count is that dictionary, right? So count of what? The count of 1. So we're putting in the key here. So 1 is the key. 1 is the key. And what value are we going to get back what is this going to evaluate to? It is going to evaluate to the value, right? Which in this case is how many times that appeared. So we put in this 1, and now we are going to get back 1, 2, 3, 4, 5, because 5 appeared in nums1, or sorry, 1 appeared in nums1 5 times. So that's what we get back. Is it greater than 0? If it is equal to 0, then this 1 didn't appear. And what we can do is just get rid of it, or not append anything, because we just come here and go to the next element in in nums2. We just look at the next element because we say, okay, that's not an intersection. It didn't appear in our nums1. If it did appear in nums1, we say, okay, count is greater than 1. So what do? We append that number into our answer list, and then we decrease the value. So now 1, 2, 3, 4, 5, we say, nah, it's now 4. There's 4 remaining ones that we can use, and then we can just come back to the next element. Now we come here, now we have 1, and now there's 4. That's the value associated to the key 1, and so we say, okay, is the count greater than 0? Yes, it is. It's 4. So we're going to add x, which is our value right here, which is 1. We're going to add that to our answer again. So now there's 2 1s. Okay. Then what we're going to do is we're going to decrease the number of appearances in this nums1. So now there's only 3 valid ones remaining. And then we go to the next element. The next element is now 3. And then we say, okay, we're going to check 3. And there's 1 3 here. So there's 1. So we append 3. We decrease the number of available 3s to be now 0. Then we go here, look at this 6, and say, okay, 6. We say, we put in 6 as the key, we get 0 back because 6 is not in this nums1. Then we don't do these two, we don't append it, and we don't decrease the number of appearances. We just come here and go to the next one, which is 8. Okay, that's how this works, and we keep doing that through all of the numbers elements in nums2, and then just return that list. Love it. Amazing. Okay, so time complexity is m and n, so those are the number of elements in their respective arrays, right? nums1 and nums2, the length, and so we need to iterate through each of those elements. So now space complexity is the minimum, which is why we're doing all that trickery, of m or n. So we're not creating extra space that we don't need to. Amazing. Okay. So now looking here. Let's see. So we sort it. We get this. Okay, this is my solution. We already talked about this one. This is the way I did it. Kind of curious. Okay, well, and this is something I haven't been really focusing on in my videos, is what's the time complexity and what's the space complexity. And the reason really is, first, I really want to learn the algorithms. I want to learn how to do these Leetcode problems. I want to learn the different algorithms, how to apply it, how to figure out how to actually solve the problems. And then later, once I get kind of good at Leetcode, I can then kind of start to more seriously focus on understanding how to critically analyze the time complexity of a solution that I come up with. I have the general idea in my head, right? Like I know, okay, if I'm iterating through each of the elements, that's O of n. If I'm able to cut it in half each time, that's log of n. If I have an operation I have to do n times, but then each time I look at an element, I have to do another operation. Okay, that's n times that other operation's complexity, right? So I have the general idea, but sometimes I don't have the rigorous kind of like mathematical, um, like coming up with m log of m. I think I could come up with that, but would I have thought m log m and then plus the n log n? I mean, when you get into the pluses and how all of that operates, I'll definitely need to focus on that more, but I feel like that's kind of like a future thing. I should focus first on the algorithms, make sure that I'm getting comfortable being able to apply different algorithms to solve problems, then maybe move on to that more scientifically being able to analyze a solution to make sure that I really nail down that portion as well. So, what is the time complexity? So let's just think about this. Like, why is this m log m time complexity? So I remember that this sort has, I believe it is m log m. So we're doing it to nums1 and we're doing it to nums2. So that's where it comes. Okay. Actually, that was significantly easier than I thought. Okay. And here we're just iterating through each of the elements. So that would be worst case scenario m plus n. And because m plus n is going to be smaller than this this right here, then that portion, this portion, doesn't matter because as m and n go to infinity, this portion here dominates and this essentially goes away, so we don't care about it. Okay. So space complexity without counting output as space. O of sorting, okay? So what if the given array is already sorted? How would you optimize your algorithm? Approach 2 is the better choice, which we can skip the cost of sorting, and the time complexity would be, okay, exactly, just as I said, m plus n. Okay, so, and the space complexity is O of 1. So in this case, we're not allocating any extra space. It's just, so here's kind of my question, like, answers. We are allocating space for answers and we're appending an element. Let's say that nums1 has a million elements in it and it's all ones. Okay, nums2 has a million elements in it and it is also all ones. Now our answer is going to be a million elements, all of ones, right? So the space complexity in the worst case seems like it would be O of n, where n is, or sorry, it would be O of min, m, or n. So you just take the minimum. That's like the worst case scenario. So he's saying it's O of 1. I'm a little bit confused about why that would be the case. But anyways, that's kind of what I'm meaning by I don't have a scientific analysis of how to actually go about figuring out space complexity and time complexity. It's kind of more of that feeling and intuition, which is something I definitely need to improve upon in the future. So, anyways, what if nums 1 size is small compared to nums 2 size? Which algorithm is better? Algorithm number 1. Yeah, okay, so time complexity. All right, so all of these follow-up questions, I'm trying to figure out where that even came from. Did it have a follow? Oh, yes, it did. Okay, I didn't see that part. I didn't see it. Okay, so if nums 1 size is small compared to nums 2 size, which algorithm is better? We're saying no, algorithm 1. Okay, sure. Why? Time complexity is O of m plus n. Yep. Which is smaller than this, so the time complexity is smaller. And the space complexity. Okay, so we're looking at the trade-offs. So that's how we're determining this. So the trade-offs, we're looking, here's this time complexity, m plus n, which is smaller than this one's time complexity. Was it? No, this time complexity is the same thing. Hold on. Sorry. This one's is larger than this one's here. Okay? But this one's space complexity is worse than this one. So this one has a better time complexity, but a worse space complexity. Now we're saying that nums 2 is or sorry, what if num 1 size is small? So there exists a small array. That's all we're saying. It doesn't matter if it's nums 1 or nums 2. This information tells us there is an array that is smaller. There exists nums 1 or nums 2. It doesn't matter which one. They are saying nums 1 in this case, but there's a drastically smaller list. Okay? Then that we can kind of say, like, okay, because it's the minimum, we can kind of relax our concern on the space complexity, and in that case we care more about the time complexity. So we can say that this one is better, the approach number 1. Okay. All right. Follow-up question number 3. If an element, or what? You can tell I'm getting tired. Oh, it's past midnight. Okay, no wonder. Um, I got off work and then I came home and I didn't even realize that it was that late. Okay. Anyways, so follow-up question number 3. What if elements of num2 are stored on disk? Actually, let me just read it and then think about it. So, hold on. Let me breathe for a second. Oh, okay. Oh, all right. There we go. All right. What if elements of nums2 are stored on disk and the memory is limited such that you cannot load all elements into the memory all at once? Okay, so how would this change? What if elements of nums2 are stored on disk and the memory is limited such that you can't load all the elements at once? So my initial instinct in this question is to think, like, are one of the, and this is the thing that I'm always like, I don't know, when I'm doing this sort, right? Like, what's actually going on under the hood here? What what's the time complexity? Like, I don't know, right? Like, that's one of the things that I need to kind of memorize. See? And I think learning the actual algorithms, if I learn, so as of right now, I haven't learned how to do the sorting algorithms, right? So therefore, sure I could spend a lot of time and kind of like memorize. Okay, dot sorted is equal to in log n, where n is the number of elements in the list. I can memorize that, but I think it is much better for me to focus my energy on learning the algorithms, and then once I get to the point where I know sorting algorithms, it kind of comes natural to me. I say, okay, well, what's the time complexity of sorting? Oh, it's n log of n, because I know sorting and I know how sorting works. So that's why I said I'm not focused on kind of like memorizing the numbers just yet. I'm not trying to like force myself to pay too much attention to the time complexity and all of this, because I need to learn the algorithms first. And then once I have a better intuition of the algorithms, I feel like the time complexity is just going to kind of come natural to me, because I do understand like what the time complexity is. I have that intuition. I know how to do it. I know how to analyze it. But if I have kind of these, I'm going to call them hidden or abstracted functions that I don't quite understand how they work yet, that's something that I will need to learn in the future, but I need to do things systematically. So anyways, where I'm going with that is I feel like this has something to do with those built-in functions that abstract functionality away, like counter, right? Or what did he call it? Count? Up here? Yeah, counter here. Like, does counter do something funky, like it needs all of the memory all at once when it's creating that dictionary? Could be the case, right? Like, I feel like that's kind of where this question is going, and I don't have that information. Like, I just don't know, because I don't know how a counter is working. And is there anything else kind of funky going on? I don't know how these sort actually works. So I feel like that's the direction that it's going. Let's read the description, see what it has to say, and then see if I was right, wrong. And then by reading this, we also kind of get a better understanding and intuition of it. So moving forward, bam, we're able to absorb that knowledge much better. Okay, so let's so here, if nums1 fits into memory, um so what if nums2 are stored on disk? So it doesn't say anything about nums1. So if nums1 can fit into memory, we can use approach 1, which stores all elements of num1 in a hash map. Then we sequentially load and process nums2. So there is something to do with, like, I think the counter does require you to be able to have all memory present, and maybe that is like in, because I need to pass it in as a parameter, right? And to pass it into the parameter, I need to be able to load the entire thing. I mean, I guess that I don't know how Python works in that case. Like, what if nums1 had, and again, I'm going to say a trillion elements, right? Like, it was some huge, like terabytes of data or something like that. It is like nums1 would just be a pointer, right? And the pointer would be whatever it is, 64 bits, something, I don't know. And so I have a pointer, I just pass in the 64 bits, and that's the only thing that's passed into the function, and then the function is able to load in as necessary. That's how I would assume that it's implemented, so I don't think that would be the problem. Okay. If neither nums1, nums2 fits into memory, we split the numeric range into numeric subranges that fit into memory. We modify approach number 1 to count only elements which belong to the given subrange. We process each numeric subranges one by one until we process all numeric ranges. For example, okay, our memory can store up to 100 elements. We split the ranges like this. Okay, that doesn't quite answer my question of like where does it fail? Like what? Okay. I mean, all right. Well, I guess I'm a little bit, yeah, I'm a little bit confused, like why and how this, like, maybe I can just, oh, let's, copy. Let's, get rid of you, and then like this. See if ChatGPT just kind of automatically knows what I'm wondering. Great follow-up question. Okay, so use a hash map to count the elements. So num1 is usually smaller and manageable. You can read nums2 from disk in small chunks. Each chunk implementation. Can you tell me exactly where it would fail if nums1 or 2 was large? Like, where is this failure occurring? Like, what is the point at which in your original memory usage? Okay, so it doesn't like the sorted for some reason. Sorting very large, especially in place, can be memory intensive and could fail. Okay, so I guess it doesn't like that. So here it's not sorted, and we're just kind of like reading it in line by line. So okay. Interesting. Well, awesome. Cool. This was a fun problem. I like his solution. Like this was really creative. I like that. Anyways, thank you guys so much for watching this video. I'm going to be it's it's not actually Saturday. It's Friday. I always just go by the actual day. I don't the day starts when I when you wake up. That's the way I say it. When I was working a swing shift or night shifts, it was always like, when does the day start? And I just decided, nah, it starts when you wake up. When you go to sleep, it's that continuous time of block, because people would say, oh, it's 12:01, it's today, meaning actually tomorrow. Anyways, so today is Friday. Don't be fooled by this. So Anyways, where was I even going? Oh, right. So tomorrow I am going to be. I didn't mean to click that. Tomorrow I is the weekend, so I'm gonna be hitting these Leetcode problems. Bam, 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 bam. Or also I need to do more of those project videos. So I'm probably gonna do Java and JavaScript. Those are more like conversational, just playing around, having a good time. So I'm going to be making more of those videos. If you would be interested in that, subscribe. That would be amazing. I've been getting like a lot of new subscribers, so thank you to everyone who is subscribing. And yeah, I'll see you guys tomorrow. Awesome. Anyways, thank you guys so much for watching. My name is Timothy Lee Grant, and I hope you have a wonderful rest of your day. All right. I think I'm probably going to go to sleep.